students, myself Dr. Bharti Patil, working as an assistant professor physics in Maharaja Jivaji Rao Shinde College, Srigonda, Ahmednagar. We have started our syllabus related to solid state physics related to TYBSc class, and in that we have started our chapter number 4, that is magnetism. Up till now we have seen what are the diamagnetic materials, paramagnetic materials and ferromagnetic materials. In today's lecture, we are going to see one more type of magnetic material and its name is antiferromagnetic materials. As we know that in case of ferromagnetic materials, if we see the neighboring atoms and the dipole moments present in them, then these dipole moments are get aligned in the direction of applied magnetic field. And if we plot in case of ferromagnetic materials, ferromagnetic materials, that is, if I want to show the alignment of dipoles, then these dipoles are aligned in the same direction. These dipoles of neighboring atoms are aligned in the same direction and their magnitude is also same in case of ferromagnetic materials. Then these are the antiferromagnetic materials. It means that in these materials, due to the interaction between neighboring atoms, the interaction between neighboring atoms such that if we consider the neighboring atoms, then interaction between neighboring atoms is such that their dipoles will anti-parallelly align. It means that there is the presence of dipoles, but these dipoles are anti-parallel to each other in case of neighboring atoms. Therefore, and the magnitude of the dipole is same. What is first property? That is, the dipoles are this atomic size should be same. In case of antiferromagnetic materials, dipoles are present and interaction between neighboring atoms, interaction between neighboring atoms is such that these dipoles are aligned, arrange, anti-parallel to each other, and same is shown here. Suppose these are neighboring atoms and their dipole is shown by the arrows, then these dipoles are arranged or aligned anti-parallel to each other, and due to this anti-parallel nature of the dipoles, these dipoles in an overall substance will get cancelled and hence they will have less magnetism. Due to anti-parallel nature of dipoles, the material will have less magnetism. So, due to antiparallel nature of the dipoles, the material will have less magnetization produced. Then next, this orientation of dipole or this susceptibility, these materials will have fourth property is that these antiferromagnetic materials will have susceptibility value and its value is positive but its value is low. These materials will have positive but low susceptibility value. So their susceptibility value is low but positive. So this is one more property. Then if we see in case of antiferromagnetic materials, the alignment of the electrons is antiparallel. The electrons are aligned antiparallel to each other and their magnitude is same. Already we have explained it here by considering the atom. Then next, if we see the variation of susceptibility with respect to temperature, then antiferromagnetic materials susceptibility of susceptibility of these materials susceptibility of these materials is highly depending on temperature. Susceptibility of these materials highly depends on temperature. Then if we see the behavior of the susceptibility with respect to temperature in case of these materials, if we plot a graph of variation of susceptibility with respect to temperature, then it is seen that the susceptibility will increase with respect to temperature. Susceptibility will increase with respect to temperature and at this temperature the susceptibility value will have maximum value. This susceptibility at this temperature is given by C, that is Curie constant, divided by T plus theta, additional temperature plus theta. This is the value of maximum value of susceptibility in case of antiferromagnetic materials, and this occurs at temperature called as nil temperature. It means that as we go on increasing the temperature of antiferromagnetic materials, the susceptibility value goes on increasing. It becomes higher at nil temperature, and above nil temperature susceptibility value will start to decrease as shown in figure, and at this temperature the susceptibility value starts to decrease and the material becomes paramagnetic. Material becomes paramagnetic means above nil temperature materials will be in paramagnetic form, and below below nil temperature, this temperature is called as nil, N-double-E-L, nil temperature. It is the name of the scientist. And below nil temperature, material will have antiferromagnetism, antiferromagnetic nature. So, what is nil temperature? That we have to explain here. Nil temperature is a temperature at which the susceptibility value in case of antiferromagnetic material is higher, and it is given by formula chi is equal to C, that is Curie constant, divided by T plus theta. Above nil temperature, material will have paramagnetic nature, because as we go on increasing the temperature, the susceptibility will start to decrease above nil temperature, because the thermal vibrations increases and they will destroy the alignment of the dipoles, and hence such type of behavior is seen in case of antiferromagnetic materials. And the examples of these antiferromagnetic materials is MgO, then FeO. These are the examples of antiferromagnetic materials. So, let's revise antiferromagnetic materials. Antiferromagnetic materials are the materials in which there is a attraction or interaction between neighboring atoms, and this interaction between neighboring atoms is such that the dipoles present in the neighboring atoms will align themselves in opposite manner. The alignment of the dipoles or the electrons is opposite, their spin are opposite, but their magnitude is same. The magnitude is same, but dipoles are oppositely aligned. Then the dipoles are present in them, but they are oppositely aligned. The next property of them is that interaction between neighboring atoms is such that the dipoles are arranged anti-parallel to each other. It is shown here. Then, due to anti-parallel nature of dipoles, the material will have less magnetization produced. So, the material will produce less magnetic field as the dipoles are oppositely aligned. Then these materials will have positive value as they are belonging to ferromagnetic groups. Therefore, they will have susceptibility value which is positive, but this value is very low as compared to ferromagnetic materials. Then next property is, if we draw this susceptibility of these materials. What is susceptibility? We have seen that susceptibility is nothing but the magnetization produced upon applied magnetic field, and this susceptibility value depends on the temperature. If we plot a graph of variation of susceptibility with respect to temperature, then it is seen that as we go on increasing the temperature, suppose this is the temperature scale, as we go on increasing the temperature, the susceptibility value of these materials will also increase, and it will have maximum value given by the formula C upon T plus theta at a temperature called as nil temperature. Above nil temperature, the material will become paramagnetic, because at this temperature, above this temperature, the thermal vibrations produced in the material will destroy the magnetic dipole moments arrangement. And the examples of the antiferromagnetic materials are given as MgO and FeO. Thank you.